Great. Great. So thank you everyone for coming today to the GISS lunch seminar series. I'm really happy to have Daniela Domeisen, who's a professor at ETH Zurich. She's been there for about 3.5 years right now. And Daniela has done some really nice work throughout her career looking at a stratosphere-troposphere coupling. She completed her PhD at MIT, where she worked with Alan Plum, looking at the dynamics of strat-trop coupling. And she's really produced a really nice series of review papers over these past few years that I've been struggling to keep up with because there's so much information in them. Hopefully we can get kind of a synthesis of some of those results here today. We're going to do like what we've done in the past, where Daniela, if it's okay with you, what we do is if someone has a question, they'll denote that in the chat, and then I'll unmute them, and then they can ask that. So it's more questions throughout the seminar. Yeah. Okay. So great. So with that, I'm going to mute and turn off my video for bandwidth, and I'll let you go on.
Thank you very much, Clara, and thanks a lot for inviting me. This is exciting to be here. Of course, I would love to be in New York in person, but hopefully again at some point in the future. So in this talk, I'd like to kind of give a summary of strat-trop coupling and implications specifically for subseasonal prediction. And this is some work that I've done with a range of members from my work group, but then also with lots of different external collaborators. Most of them are listed down here. So as Claire said, if you have any questions, feel free to jump in. So the contents of this talk are going to be split into 2 parts. So the first part will deal with how does the stratosphere actually influence the troposphere, just giving a bit of an overview and some examples. And then in the second part, I'd like to go into what's the stratosphere's influence that we can actually then use for tropospheric predictability. And it turns out that's not as easy as we had hoped it would then be. So I'd like to point out 2 events that probably if we hadn't had a whole pandemic the last year, maybe would have been more in the memory of people for 2020, for extreme events in 2020. So in terms of extremes, weather extremes in 2020, we had this one event in February 2020, which was a series of storms that hit the UK. One of them was Storm Ciara, and there was Storm Dennis, so on. So they had extremely high winds, lots of rain. There was lots of flooding in the UK following this storm series. And then in addition, we had devastating wildfires in Australia, and here put a picture from January 2020. But of course, these events had been going on for quite a while already in 2019. So the question for these extreme events is, what do they actually have in common? And they do have potentially in common that the stratosphere might have been helping to cause both of these events. Now, this may seem a bit far-fetched, so let's have a bit of a closer look into this. So the type of events that we tend to look into, and the most kind of exciting events that we look into are so-called sudden stratospheric warmings. There was one of them actually happening in January this year. And here I'm showing an example from February 2018, just because I kind of like this event because it was kind of a perfect event with a perfect downward influence. And what you see here is potential vorticity at 10 hectopascal in the stratosphere, so kind of mid-stratosphere. And the pink area here is high PV, so basically anti-clockwise rotation around these pink areas. And the vortex is basically here a wintertime feature that kind of rotates happily around, but then on February 12th, it was split into 2 smaller vortices. And they kind of then keep interacting and stay more or less in place, but then there's a lot of dynamics going on there following this. If you want to know more, I'm not going to say much more about sudden warmings in this talk. If you want to know more, there's a review paper by Mark Baldwin. It just came out last month. The interesting thing here that I'd like to look at is what happens at the surface after these events happen, because that's really the interesting interesting part here if you want to look at and try to understand predictability. So this was the kind of the surface impact, or at least what happened after this particular stratospheric warming event. So there was a cold anomaly here over the north of kind of northern Eurasia, and then warm in the Arctic, Greenland, and kind of over Canada, and then also warm here over large parts of Asia and the Middle East, and also Northern Africa. This is a very typical pattern. That's why I'm showing this particular event, because if you now compare this event with what happens on average, averaged over all the events that we've had, then you can see almost the same picture. So basically cold over Eurasia, then this warm in northern Canada and Greenland, and then this warm patch again here. So basically, this was kind of a textbook event that we had in 2018, which with kind of a perfect downward impact. Now, if you look at the one from this year, it wasn't actually that much of an outlier. It certainly contributed to this response. So this is the 2-meter temperature anomalies after this year's event in January. This figure is by Amy Butler that she made for a blog that we just recently wrote for NOAA. So again, you see this kind of typical pattern. So I have to warn you, this is not the pattern that we see every single time, but it happens a lot. So basically, that's why on average, obviously, you get this kind of signal. And this is related to the NAO, the North Atlantic Oscillation, which usually turns to its negative phase. So basically a more wavy, weaker jet that then leads to these types of anomalies. So basically cold and dry in the north of Europe, warm and rainy in southern Europe, and this opposite pattern here over North America. So this is the kind of signal that we expect to happen after sudden warming. And if you look at what happened after the 2018 sudden warming event, then you can really see that the NAO had been positive the whole winter, really since early December. And then really like 10 days after the event, it dipped negative, very strongly negative, and then stayed there for about a month. So this is kind of exactly what we would expect. So these kind of negative North Atlantic Oscillation events, they happen more frequently after sudden stratospheric warming events. They're also more persistent, as you can see here. When we look at how long a negative or a positive NAO event usually lasts, so basically this is how many days here does the event actually, or does the NAO actually stay in its positive or negative phase. So gray here would be the positive NAO. This would be the number of days. And the red bar would basically go all the way to the bottom here. So I'm just plotting kind of the overshoot here. So in climatology, the negative NAOs are often pretty short, or shorter than positive NAOs. But then if you look after a weak vortex event or a sudden warming event, then these kind of longer timescales dominate among the negative NAO events. So basically, the negative NAO events become more persistent after these events. They're also the weather also transitions more frequently into these negative NAO events. So this is kind of the response that we would expect after a sudden warming. The question is, how has it actually looked like in history? So this is just 1979 to 2014. So if you look at how many of these kind of persistent NAO events have happened throughout history, this is an NAO index now that goes back all the way to 1850, then you can see that we've always had this kind of variability in terms of how many of these persistent events actually happen throughout history. And basically this is one bar for every winter. Now, the nice thing is basically, since sudden warmings often have a downward impact, but we don't really know what happened in the stratosphere anytime before like the 1950s. But we have time series for when these NAO events happened. We can try to reconstruct what happened in the stratosphere before the 1950s. And this was an attempt to do this here. There's lots of lines on here, so I'm just going to walk you through quickly. So basically, this is the red line here is the kind of smoothed sudden warming occurrence. So basically all the sudden warmings that had a downward impact. You can see basically there was nothing in the 1990s. This is a kind of a well-known kind of sudden warming drought. And the dark red line here is kind of the estimate just based on the actual NAO persistent events. And since these two lines are reasonably well correlated, basically we just extended this estimate all the way back, and you can see that we can at least try to extrapolate how many sudden warming events occurred in every winter all the way back to 1850. This is, we can't really compare that to anything, but basically it can put these 1990 sudden warming drought into perspective, because there was basically nothing. So this can then tell us that basically in the 1990s, the most persistent absence of persistent negative NAO events, and by extension, possibly the longest absence of sudden warming events in more than 150 years. So this was really an exceptional time. We don't really know if this has anything to do with human influence or not. It might just be natural variability. We don't really know why this has happened, but you can see there's been quite some variability also in the past, for example, in the early 1900s. So if you go back to what that might have meant for surface impacts all the way back to this time, during decades when we had a lot of sudden warming events, or when we had few sudden warming events, then we can look at, for example, and I showed you this.
Hi, Daniela.
Yes,
sorry.
Tell me.
Yeah, I just have a question on the previous slide.
Mm-hmm.
So for the dearth of warmings in the 90s, was that also accompanied by significantly weaker planetary wave flux into the stratosphere? Do you see an anomalous pattern in that, or is this more something that was going on within the stratosphere itself?
I think it was also related to weak planetary flux. I haven't seen a consistent analysis of that, or haven't done one, but it's probably related to a range of different factors. I mean, people have cited like ENSO as a potential factor. People talk about the solar cycle. I'm not really sure about that one. Other people in the audience might know more about that. So I do think it's probably related to reduced planetary flux indeed, but I haven't seen a systematic study of how that looked like.
Thanks.
Sure. Okay, so then if you look at the actual kind of occurrence of extreme events after that, here's an example of colder outbreaks after weak vortex events. This is a study by Eric Kolstad, where he looked at kind of the anomalous number of cold days. So basically just translating this cold anomaly into, does this actually lead to a colder outbreak? And basically all the way to like 2 months after a sudden warming, you can still see that there is this kind of cold anomaly here and this warm anomaly here. And you can go all the way up to double the number of cold days as compared to normal here in parts of Siberia, for example, and at least 50% more cold days, up to like a month or more after the sudden warming. This has impacts on real lives. So Andrew Charlton Perez had this couple of nice studies where he actually looked at mortality. Turns out sudden warmings actually have real life consequences, where there is huge health impacts on mortality in the UK of these events. This isn't just the case on land. There's also impacts over the ocean. One thing we've looked at is marine colder outbreaks. Marine colder outbreaks are especially important in kind of places over the ocean, especially in the Arctic Ocean, where there's lots of infrastructure that's being developed. And especially here in these areas, it used to be a lot of fishery. Now it's oil rigs and wind farms and so on, where basically these colder outbreaks can lead to, for example, icing that can sink entire ships. This has kind of these extreme impacts. And after sudden warmings, you indeed get this much higher frequency of marine colder outbreaks over kind of the Barents and Norwegian Sea. So these can have extreme impacts, especially in terms of the so-called polar lows, also called Arctic hurricanes in the Barents Sea. So these are pretty kind of small scale, very small scale cyclones that can live for just a couple of hours, and they're extremely destructive. So basically, if we've done a project with some stakeholders who want to know basically when do we have a higher risk for these polar lows, because basically it really limits their working ability in this Arctic environment. This is how I learned about interesting work guidelines for the Arctic, where basically they have different guidelines for how long they can actually work outside, depending on the weather and the temperatures. And I assumed they would be like, okay, so in these conditions you can work 1 hour, in this condition you can work, I don't know, 2 hours. But these limits of times are actually in minutes. So I was very, very impressed when they said, like, okay, in these conditions you can actually go outside for 1 minute versus 2 minutes. So I was, I never really thought of sudden warmings having such real life impacts in terms of the kind of the Arctic infrastructure. I found that pretty impressive. So if we see these, so basically sudden warmings can have high risk for colder outbreaks. Colder outbreaks can have a higher risk for so-called polar lows. So we have a lot of kind of risk that we may potentially anticipate if we can actually make a better prediction. We recently looked at other extreme events. So basically, what are extreme events that can potentially happen following these sudden warming events or caused by sudden warming events? And so basically, we found a lot, like, so I already mentioned the marine cholera outbreaks, these cold extremes. There's sea ice changes, there's ice melting at times. There's flooding. So, for example, there was flooding events in Spain after one of the sudden warmings. There can be extreme winds and so on. We know much less about the southern hemisphere. So this is one thing that we're currently looking at. There's a couple of studies already out there, but we're really trying to understand what happens in the southern hemisphere because we just have much fewer sudden warmings happening in the first place. So this can have real impacts on extreme events. So basically, we should understand better what happens there, and we should be able to try to predict them. So, but first I'd like to have a quick look at kind of the opposite of sudden warming events. So what I showed you is for sudden warming events, we have this weaker jet stream over the North Atlantic and these kind of anomalies. If you have a strong vortex, so stronger than normal polar vortex, we get instead usually positive NAO, very strong jet into Europe. And this obviously has very different impacts on temperatures, on rainfall, and so on. So these are some of the anomalies. They're almost opposite to what we had before for the weak vortex events. And as you can see here is that the surface temperature signature of these strong vortex events is also almost opposite. So you remember from before, basically we had cold temperatures over Eurasia. This is now warm anomalies. So basically the exact opposite to what we had before. This then leads to a much stronger jet, as I said, that comes into Europe kind of further north, or some people call the positive NAO the normal NAO. So basically the normal places get lots of rainfall, like Scotland, Norway, these places where you would actually expect a lot of rainfall. But then if you have a very strong vortex, this can really turn into extremes where, for example, you had these storm series that I just talked about initially. This was associated with an extreme positive Arctic oscillation. I think they even had to kind of expand their scale here because that was really a record rally of the Arctic oscillation that they had in February 2020. Now this event, this extreme strong vortex in the stratosphere in February 2020 was, as I said, associated with the storm series. It was also associated with an ozone hole in the northern hemisphere that was much larger than what is usually observed, especially for the northern hemisphere. So here, as you see, the ozone mass mixing ratio for March 2020, and maybe I can show you this as an animation, where basically oftentimes you see very thin ozone going over really large parts of the Arctic, sometimes going all the way into lower latitudes. So I've been telling my students to put on sunscreen if they go outside. Obviously, this is an issue that other places have as well, especially in the southern hemisphere. Now, does that mean that the stratosphere actually kind of dictates the weather at the surface? So basically, now that we know, like, okay, we always get this cold in Eurasia after the weak vortex, we get the opposite after the strong vortex. So do we actually know, does this always happen? So this should allow us to actually make a prediction. Now, it turns out it's not quite that easy, unfortunately. But in general, if we average over all events, notice here is 24 events, we see exactly the pattern we would expect. This is kind of the negative NEO associated with blocking over Greenland, and then lower geopotential heights here coming into Europe over the more southern part of the North Atlantic. But this composite is actually made up of different events. About 2/3 of the events really show that negative NEO. These are these events, and as you can already see, these are contained in all the sudden warmings. You can see for these, the response is much stronger. But then, if you look at the remaining events, those actually have almost the opposite response, and certainly not what we see here. So basically, about 2/3 of the event really show that negative NEO response that we would expect, the cold over northern Eurasia. But about 1/3 of the events don't actually show that. We don't really know why this is the case. We also can't predict which ones are the ones that actually have the expected response and which ones don't have a response at all, or which ones have almost the opposite response. Interestingly, if you just look at persistent negative NEO events throughout all the winter, about 25% of these are indeed preceded by a sudden warming event. So once you have a sudden warming event, 2/3 of those have a negative NEO, a persistent negative NEO. But if you have a persistent NEO itself, and we can go back to the stratosphere, and about 25% of those have actually are preceded by a sudden warming event. Okay, so
sorry, I just have
yes.
one question on that. So on that composite on the right, just I guess the obvious question is, when you further petition to El Nino, La Nina, you don't see kind of a consistent relationship in those. Is that?
So if you just take the El Nino events, then you usually get a negative NEO.
Yeah.
You also get more sudden warmings. If you look at La Nina, the signal is much more muddled. So basically, I would say among these 14 events in the center, probably a lot of them are El Nino.
Yep.
For La Nina, it's much less consistent. So basically, La Nina events can go either way.
Yeah.
And depending on whom you ask, La Nina might not have a strong teleconnection to the stratosphere or Europe in the first place. I mean, there was Lorenzo's study, right, showing that.
Yeah, thanks.
So yes. Mm-hmm. So to what extent does the surface impact actually depend on the troposphere itself? So because basically they'd always been looking in the stratosphere, like, okay, why do not all events have a surface impact? Maybe there's something different happening in the stratosphere. But maybe there's also something different happening in the troposphere. Maybe the troposphere is just not allowing the downward propagation of the signal. So we've been looking at that, trying to figure out if the troposphere plays a role in which events actually get to have a downward impact and which ones don't. So we've basically made a so-called Baldwin-Dunkerton plot, a dripping paint plot, where we're here plotting. This is a composite of all the events. We're plotting geopotential height anomalies for the Atlantic sector here. It looks very similar if you just plot the northern annular mode. That's a very similar picture, but basically you can see, okay, here's the event, kind of propagates down to the lower stratosphere reasonably quickly, and then persists in the lower stratosphere, and every once in a while it kind of drips down into the troposphere, but not all the time. And again, this is an average now over overall events. So then we stratified these events according to what the troposphere did here at the time of the sudden warming. And we stratified it up in terms of the weather regime that was present around the onset of the sudden warming event. And it turns out you get a pretty different picture depending on what happens around the sudden warming onset. Actually, the most conducive to a downward response is when you have a European block at the onset of the sudden warming. You get a lot of these kind of downward drips afterwards. If you have Greenland blocking at the onset, that mostly means that the responses afterwards mostly shut off. And if you have any of the other regimes, mostly solar regimes or Atlantic trough, then you get a little bit of a downward impact. Notice that this statistics are pretty small on these composites. We tried to do all the statistics that we could for this, but then again, just note that there's always only 5 or 6 events. So it will be interesting to see how that plays out once we have more events available. Basically, it seems that this one is robust. Basically, if you have European blocking, oftentimes you actually, at the onset of the sudden warming, you often afterwards also get a response to the sudden warming. So there's lots of different things that might be responsible. So it's one of the reasons for having a strong impact in the North Atlantic region is also having to have a long-lived response here in the lower stratosphere. That's also another factor. But there seems to be a lot of different factors that play into this. Like can the troposphere actually respond to the stratosphere? Currently, I kind of view it as the stratosphere just being there the whole time, kind of suggesting to the troposphere what to do. And the troposphere then basically decides by itself, do I actually want to take up that signal? Do I actually want to do what the stratosphere is suggesting to me that I should do? And it kind of works in 2/3 of the cases. In the other third, it doesn't really work, or it even works the opposite way. So I've talked a lot, as I said, about the northern hemisphere now. So what about the southern hemisphere? I showed you this example of the wildfires in Australia. And there was this nice study by Lim, where she did composites of all the different times when the vortex in the southern hemisphere had been breaking down early. So kind of wasn't in the southern hemisphere, you don't really get these strong sudden warmings, but you can get early final warmings. So the vortex can kind of break down earlier than usual. And she put together 9 years that had such an early breakdown of the vortex, earlier than usual. And she saw that basically you end up with higher daily maximum temperatures over Australia and less precipitation. And just in the year when she published this, we had a very early breakup of the polar vortex, and we had these extreme wildfires, especially here in this region over Australia. So there might have been some connection between what happened in the polar vortex with this early breakdown and the wildfires in Australia that were observed that year. Of course, that was also helped along by the sign of the Indian Ocean dipole that year, and of course climate change. So there's lots of factors, of course, that have to come together in order to really fuel these wildfires. But the stratosphere might have played a role in this. So as I said, the extreme wildfires were potentially kind of aggravated by the fact that the stratosphere had an influence that year. So in summary of that first part, the stratosphere can have a significant surface impact. About 2/3 of the sudden warmings have kind of this typical NAO impact. And it's not really clear what actually causes this diversity. We don't really understand fully what this would actually mean in terms of the diversity. We don't really understand why particular events have a downward impact, and we also can't really predict that. So that's gonna be the part 2. Can we actually predict the stratosphere's influence on tropospheric predictability? If there are any questions for the first part, I could answer them now, or I can also go on either way.
Hi, I'm Jimmy Booth. I had a question. I'm just thinking about the pattern of the temperature anomaly that shows up at the surface, and I was wondering, when you go up to 10 hectopascals, is there any zonal anomaly in the climatology? Or when you're that high up in the stratosphere, is there no imprint of asymmetries that we know are in the troposphere?
Yeah, that's a very good question, and this is something that's not fully resolved. So basically, there's been a lot of studies trying to link the geometry of the vortex at 10 hectopascal to the actual geometry at the surface, with no real conclusive results. So basically, it seems that to a certain extent, it's the geometry that's it is related in kind of guiding the jet stream. So, for example, you know, all these newspaper articles that are like, oh my God, the polar vortex is coming, and so then you have like a polar vortex that's maybe shifted slightly over North America, and that kind of guides where the jet stream can go, where the eddy-driven jet can go over North America, and that determines where you end up with cold temperatures. But there's no real clear, there's not such a clear connection. So, for example, basically, you always get the impact over the North Atlantic. You don't get it over the Pacific. Like, why would this be? And this, I think, is mostly related to not so much the geometry of the vortex in the stratosphere, but mostly the geometry of the jets in the troposphere. So basically, sometimes the parts of the troposphere are just more receptive to a stratospheric signal than other parts.
Nice. That's great.
Yeah. Rather unresolved question.
Related to that, with the really strong vortex, you have these storm clusters, and there's been papers about perhaps the clusters are self-maintaining due to wave breaking. Has there been work on how the stratosphere influences or guides where the upper level wave breaking occurs? You know, there's these studies by Joaquim Pinto that just point to wave breaking and driving the clustering. I was just wondering if people have connected the orientation of the breaking to the stratosphere.
Very good question. To be honest, I'm less familiar with this, but I feel like there's kind of a disconnect between kind of the large scale stratospheric community and kind of the synoptic scale community, kind of like, you know, the tropospheric weather community. So we're currently trying to bridge the gap. I feel like there's a strong language barrier, but we're working on it. But to be honest, it's also just really difficult to connect those. I mean, we try to look at, you know, different types of, you know, tropopause folds after sudden warming. Like there's no, it's really hard to see a direct signal onto kind of the synoptic scales that we see in the troposphere. So I think making this connection is just really hard. So yeah, it's basically, I guess, Joachim's work and Andrea Lang's work. Some of those people have done some nice work on that, but that's not fully understood yet. I mean, we know that synoptic eddies are affected by the stratosphere. But basically, the way the stratospheric community has talked about is mostly in terms of, okay, we need the synoptic eddies in order to react, or in order for the troposphere to be able to react to the stratosphere. But, you know, how exactly these waves might be guided, how exactly they might be breaking, I feel like that's a lot of open questions remaining there.
Okay, well, thanks a lot.
Thank you.
Great. So we have one comment, actually, Danielle, in the chat. David, do you want to unmute yourself? Okay.
Sure. So, Danielle, you raised the question about the 1990s, and some people have suggested a potential solar influence. Well, the solar influence then was relatively weak compared to what people think it might have been in the past. And perhaps a fruitful time to investigate, if someone hasn't done it already, is the Little Ice Age time period, roughly between the 16th and 19th centuries, because people have put together a reconstruction of what the weather anomaly, the surface weather pattern looked like during the Little Ice Age. And they said that in general, there was a predominance of a strong high over Greenland. And then the anticyclonic flow brought northwest winds down over Western Europe. That also is a time period, at least part of it, in which people think there might have been, you know, the so-called Maunder minimum. There might have been reduced solar insolation. Nobody really knows that for sure. But and the other thing that raises is, if indeed the climate was colder, though maybe not globally, but colder, maybe what's going to happen in the future when the climate gets warmer is you'll have the inverse of that Greenland high. And therefore, that might also suggest something about the stratosphere, what it will look like.
Thank you. Interesting. Yeah, I have not looked at the life age in that connection, but that's very interesting. I'm gonna have a slide at the end of like what, you know, the uncertain future of the stratosphere and how that might influence the troposphere. But basically, we don't really know because there's lots of different effects at play in terms of how the stratosphere might change. In terms of, for example, the changes in the jet stream, which will lead to changes in planetary wave propagation, which will change the stratosphere. At the same time, you have greenhouse gases, so the stratosphere might cool. So you'd expect a stronger polar vortex. So basically, the models have no idea what to, like, if you look at CMIPs, the models don't really know what to predict there. But that would be an interesting comparison with the past. Thank you. Okay. Should I go into the predictability part then?
Yep, sounds great.
Okay. So in terms of predictability, what we've looked at is in terms of what can we actually predict. So we looked at, for example, seasonal predictability. This is a map using the kind of the German Weather Service seasonal prediction model that they currently have in operation. And this is an initialization in November. And then we're looking at prediction skill for December to February. And kind of unsurprisingly, the tropics have a much better predictability than the exotropics. And actually, I always show this to the Europeans. Basically, Europe is kind of a blue hole of, unpredictability. So this is why, after all, Europe is a very interesting place to try to make predictions. But as you can see, also parts of North America with very poor predictability. So we're trying to see if you can improve that. And especially for this part of the Northern Hemisphere here, we might actually have a benefit from using the stratosphere. So you looked at a range of different teleconnections on all the different lead times, and this is kind of where the stratosphere comes in. Although the stratosphere does act on lots of different time scales, so we may be able to use it also on other time scales, but this is kind of the time scale that I've been focusing on. So go all the way from weather forecasting to climate projections, and here are a range of different kind of factors that we may be able to use in order to make better predictions then. So the nice thing is, and why we want to use the stratosphere for predictability, is that the stratosphere is more predictable than the troposphere. It generally moves much slower, and it does seem to have an influence on the surface, so we should be able to use it for prediction. So this is just a plot showing that, officially, according to predictability metrics, the stratosphere has a higher predictability than the troposphere. This is the prediction limit. So basically, when our correlation skill score falls below 0.6 in this case, this is a pretty arbitrary measure, but this is just in order to compare the stratosphere to the troposphere, and you can see that we're here. This is the multi-model mean. The stratosphere would then, according to this measure, be predictable out to about 16 days, while the troposphere is more like, what we're used to, about a week. Now, this doesn't necessarily mean that there's any causal relationship between the two. It's just that the stratosphere may be moving slower, or that models that have a good stratosphere also have invested a lot into the troposphere. So basically, this is the multi-model mean, and these are all the different prediction models here, which nicely fall onto one line. This relationship, and this is one of the reasons why you can say this is really not causal necessarily, is that the same relationship holds for summer. This is now for June, July, August, and we see the same type of relationship, although we wouldn't really expect the stratosphere to have a downward impact. So if you look at the stratosphere itself and its prediction limit, then we can say the sun warmings themselves are actually not very predictable, at least not beyond 1 or 2 weeks. This is the percentage of the ensemble members that are able to predict a sudden warming event at a certain lead time. So this is like 1 to 5 days before the event, 10 to 6 days before the event, and so on. So you can see shortly before the event, at least some of the high-top models that have a well-represented stratosphere are basically always able to predict when the sudden warming occurs. But this drops very quickly. And actually, some models have absolutely no skill in doing this. Mostly those are the ones that don't have a well-resolved stratosphere. And you can see that basically, after about 2 weeks of lead time, the false alarm rate, which is this black bar here, is about as high as the hit rate. So basically, after 2 weeks, we can't make any kind of prediction if a sudden warming is happening or not. So while we may not be able to predict the individual events, we may be able to predict what happens in the troposphere, because if you have a certain probability of an event, we may be able to predict what happens afterwards, especially since, as I showed, that tropospheric effect then lasts for 1 or 2 months. So the nice thing here is that the models are actually pretty good at that, at least in the average response. So I'm plotting here. Again, you've seen this plot before. This is weeks 3 and 4 after initialization. This is here error interim. And this is the multi-model mean from the S2S prediction database that was put together by Frédéric Boutard. And you can see this comparison between the multi-model mean and kind of our truth. And basically, you see the same overall signal that we would expect. So basically, overall, averaged over all events, we have a pretty good handle on predicting what's happening in the troposphere. If you just look at strong vortex events instead, so basically the opposite, we also see the opposite signals. The model are able to reproduce this. So on average, we're actually pretty good with these models in predicting what's happening. But now the question is, can we actually predict what happens after one particular event? Because, you know, if a sudden warming happens and it's the same thing every time a sudden warming happens, and all the journalists call and say like, okay, does this now mean that we're going to have snow and cold? So it turns out that after individual sudden warmings, we're actually not that good at predicting what happens in the troposphere. If you really compare for each event, did the model actually predict the right thing after the event, then for the lower stratosphere, we're still pretty good. So this is a comparison between what happens after a weak vortex event and just a control. This is for the Northern and remote here. So basically, if the bar is red, that means we actually have a higher predictability after the event happens. If it's down here in blue, that means we have a lower predictability after the event happens. So once we go to the lower stratosphere, already we have a higher predictability after the event. If you go further down to the surface, then this becomes much worse. You can see there's huge error bars. Some models have a worse prediction skill, even for the hemispheric pattern. But in general, they were still in the positive, but as you can see, it already becomes a lot more difficult. Now, if you look at this for strong vortex events instead, then you can see a similar picture, maybe slightly reduced already here in the lower stratosphere, also generally positive at the surface. So it's a bit less clear for the strong vortex events, but it's almost more clear here at the surface for the strong vortex event. So basically, if we have an event in the stratosphere, in general, if you look at the hemispheric pattern after an individual event, we're reasonably good at predicting the right sign of the response. So that's a good start. But if you look at the actual local distribution, the hemispheric distribution, now all the red and yellow areas mean we get a better predictability after weak vortex events. All the blue areas mean we get worse predictability after weak vortex events. And you can see the exact area where we would have hoped to get increased predictability, because Europe is so strongly impacted by the NAO. This is exactly a region where we get less predictability after the weak vortex event. And if you ask me why this is, we haven't fully solved this question. We're still working on this. So basically, we're probably able to forecast a large-scale pattern, more or less the NAO. We're basically not able to predict what happens to 2-meter temperature, which this is in this case. We're doing slightly better, at least for Europe, if you look at predictability after strong vortex events, or predictability is slightly higher after strong vortex events in general. So, but this is certainly an open question. So why is this predictability really not significantly increased? We would have hoped to basically see clear signal, much better predictability. And we'll basically just kind of scratch the surface of this problem of why we can't really predict it. And of course, all the forecasting centers want to try to understand why this is the case, because the times after the sudden warming events are often their biggest forecast busts that they really can't resolve. One thing we found so far, and that doesn't yet solve our problem here, is that models often tend to actually overpredict the surface response of the stratosphere. This is a paper by Erik Kolstad, where he looked at the model errors, the typical model errors that we see in the troposphere. And so note, this is not a negative NEO, this is the model error that we see. It looks like a negative NEO. So we kind of identified the major model errors that we get, and this major one looks like a negative NEO. And it turns out whenever this happens, this is preceded by a weak vortex. So basically, whenever we have a weak vortex, this is now in the ECMWF model, then we end up with an overprediction of the negative NEO. So basically, the model is like, oh, there's a sudden warming, I need to put a negative NEO in the troposphere. And he does that, but often it's basically too confident in what it's doing. And the exact opposite happens when we have a strong vortex event, or actually when we have this type of model error, which looks like a positive NEO, that's most often preceded by a strong vortex. So we actually have an overprediction of the model. The model becomes too confident once it sees what's happening in the stratosphere, and then often it actually gets it wrong. This doesn't really solve our problem for why is predictability lower over Europe, but this kind of gives us a start for why this might be an issue, or what some of the things at least that models are doing wrong. So if you look at other timescales, I've now talked a lot about this kind of S2S timescales, or the weeks to months timescales, but the stratosphere actually obviously varies on lots of other timescales. For example, we have quasi-biennial oscillation on several year timescales. We obviously have climate change in the stratosphere. And I said this briefly in response to David's question. So what do the scenarios actually tell us? What does CUMATE tell us about stratosphere-troposphere coupling and about the evolution of the stratosphere itself? Now, for the Northern Hemisphere now in particular, it's really unclear if there's any trend. So basically, this is the change in the wind. So basically, how will the vortex in the stratosphere develop in the future climate? This is a paper by Alice Simpson, where she looked at how that might actually change. And you can see that, some models predict a stronger polar vortex in the future, and other models predict a weaker polar vortex in the future. And then there's a lot of models in between that basically don't have a clear response. And also, as you can see, obviously the error bars are huge because the models don't really have a very confident response towards what's happening with climate change. So huge uncertainty, and this is probably, as I said, linked to the fact that we have, on the one hand, greenhouse gases which are cooling the stratosphere, yielding a stronger vortex, and on the other hand, we have changes in planetary wave propagation due to changes in the troposphere that are related to climate change as well, and that might actually increase wave propagation and therefore actually weaken the vortex. So basically, the models have this trade-off between several processes, and it's really unclear how these are going to work out, how these are going to balance out. So this is just a brief excursion for climate change. So I'm going to summarize this part. So the average downward response we can predict pretty well, but for specific cases, the models perform very poorly. So in conclusion, over all of this, the stratosphere is more predictable than the troposphere, but it remains more difficult to predict extreme events beyond these deterministic timescales. But the stratosphere might be able to help, because the stratosphere has a significant influence on surface weather, maybe potentially used for subseasonal prediction, but we're still not there in order to actually make better predictions. Actually, we're making worse predictions after these events, although we feel like we know what's supposed to be happening. So the models are not yet able to predict that diversity that we see in the troposphere in response to this stratospheric forcing. We're working on trying to figure out what's wrong in the models, but also can we get a better understanding of the coupling that would then help us to better be able to make these predictions. And with this, I'd like to thank you for your attention and your questions already, and happy to answer more questions. Thanks.
Great. Thank you very much, Daniela. That was a really nice summary, a lot of information. So I'm going to just wait kind of a few minutes. If people have any questions, just you can enter that in the chat. So I guess as we're waiting, yeah, I found, so I guess the over prediction, the slide where you showed the over prediction of the model, it was maybe about 5 slides ago. So I didn't catch that. This is something, this kind of overconfidence you said of the models, once they are kind of tending towards having a warming and then they kind of overestimate the surface response. Is this specific to one model? I didn't know if this was, or
this is now, this is in the ECMWF model, okay, which we consider one of the best in terms of, getting the stratosphere right, having good stratospheric resolution and so on. We haven't tested this in other models, so this would be basically the next step, so like, do all models have that problem? Probably not, because otherwise we might not end up with this exact pattern that we saw in this slide here, because this is the model average over all the different subseasonal prediction models.
Yeah.
So yeah, this is very specific to one model, but to be honest, this is one of the models that we work with a lot, and that we're really trying to understand. And ECMWF is basically providing these forecasts to basically all the European weather services that are then using that forecast, which is why then the Swiss Met Office ends up calling me and saying, like, what's happening, because our forecasts have never been this bad. And basically then they need to go to the government and justify why their predictability has been lower in a particular year. And it's basically often because there was a sun warming.
Yeah.
And this can be an issue.
Yeah. Great. Makes sense. So I have one more question, but I'm going to reserve that to the end because we have actually a few points and questions that were raised in the chat. David makes the comment, models, maybe David, yeah, you can ask.
Yeah, an assessment was done a few years ago about what the variability was in seasonal predictions in models and how that compared to the variability in the real world, and what the variability was related to. And what they found that models, and these are obviously now coupled atmosphere ocean models, models tended to have too much of their variability associated with ENSO events compared to the real world.
Yeah.
I don't know if that relates to the issue of them overestimating negative and positive things, NAO events. But in general, models don't necessarily do a very good job in the causation of their variability, again, in general, compared to the real world. At least that was the result a few years ago.
Interesting. I'm not familiar with that study, but the stratosphere is certainly impacted by ENSO, and this is one of the issues that we have, is that the ENSO teleconnections are much too linear. So basically, if we have the models basically react way too linear. Basically, you have an El Nino, you get a certain response. You have a stronger El Nino, you get a stronger response. You have a La Nina, you get the exact opposite response. But that's not actually what's happening in the real world. So I feel like there's a lot of kind of non-linearity in there. There's a lot of non-stationarity in there. So I could see if they have too much of their variability associated with that particular effect, you might be over-predicting some of these effects. So that might be related. Interesting. I might ask you about what that study was.
Great, thanks, David. So then we had a comment from Chris Vargan. Chris, do you want to unmute yourself, or do you want me to read it?
Great. Okay, I'll just read my question. So yeah. How well do we understand, this is the part one question, how well do we understand the mechanism involved in the impact of SSWs on the troposphere? I haven't really been following the latest literature on that. I have some idea, but how much do we know about the mechanism?
Yeah, I mean, not enough yet, but basically we know that we need coupling by both planetary scale and synoptic eddies. So basically, if we don't have either of those, we basically get the jet to shift in the wrong direction, or not enough variability. So we know there's a coupling there, a wave coupling associated there. So basically, by warming up the lower stratosphere, you're impacting the wave propagation in the troposphere. But there is different theories for what how that downward coupling could actually work. Like, I mean, in the old times, people were just basically doing PV inversion and then looking at the tropospheric response, but it turns out that's not the whole answer, because somehow it's not clear why this response should then live for like 2 months in a row, right? Because that's not actually the memory of the atmosphere. So there seems to be some feedback effects, either through the long response in the lower stratosphere, but then also through feedback effects in the troposphere through probably synoptic scale eddies. But how exactly that works, not fully resolved.
I see. Thank you.
Thanks.
Thanks. So Ron has a question about wave number 1 versus 2. Ron, do you want to unmute yourself?
Hi. I apologize if Jimmy asked this question already, but my understanding for sudden warming events is that there are 2 general categories. The wave number 1 events, and then there are the kind of the split vortex wave number 2. And I'm just wondering if that has any influence on how much predictability there is.
There's an influence on how predictable the events themselves are. So basically, wave 2 events are much less predictable than wave 1 events. This we don't really have enough events to show that this is strongly significant, but it seems that wave 2 events in general are less predictable. This is possibly related to resonance effects in the stratosphere, which may just be not very predictable, why wave 1 events often happen through a constant erosion by the waves of the vortex, and then eventually it just shifts off the pole. While when you actually split the vortex in 2, that seems to be a much more dynamic event in a way. So, people have argued that these might actually be completely different phenomena. But then again, they're probably linked, because wave 1 often does a lot of the work of weakening the vortex, and then wave 2 just kind of comes in at the last moment and kind of takes advantage of the vortex already being weakened. So it's much harder to predict when these wave 2 events happen. In terms of surface predictability, we don't see a strong difference from what we've looked at so far, but we haven't really done a systematic investigation of that.
Okay, thank you.
Thank you.
Great. I just had one kind of quick question, just thinking about CMIP6. I know the figure you showed from Isla before, showing just the total spread and the response of the vortex strength. Presumably that was for the CMIP5 models, I think.
Yeah, that was CMIP5, yes.
Exactly. So yes, and I know that Blanca has done kind of the same, but looking at sudden warming frequency. I guess just, because it's interesting to ask, have you looked at some of the high ECS models, and have you seen for the higher ECS models any kind of correlation between polar vortex strength changes in ECS, or is it much more complicated than that because of all the interplays of the effects that you just described?
To be honest, I haven't looked at it, so I wouldn't be able to give you an answer of what it looks like, but it seems like we still don't really know how, sudden warming frequency will change in the future. Also, it seems like sudden warming frequency is not perfectly related to vortex strength over the winter, because there's different evolutions, different variability. So as far as I know, we don't have a conclusive answer, but I also haven't looked at these models.
Great, thanks.
But yeah, it will be interesting what comes out of all the further studies looking at CMIP6 in particular, and especially the coupling with the troposphere.
Yeah, great. So we're kind of about 5 minutes past 2 o'clock right now. I want to thank you again, Daniela, for giving a really, really nice talk. A lot of information here. So I want to thank everyone else too for joining. Again, this is being recorded, and it's going to be available on the GISS YouTube channel. So if anyone has any questions about accessing that, just please let me know. And thanks again, Daniela, for a really, really nice presentation. So
thanks, everybody. Thanks, Clara, for inviting me. That was really great.
Great.
Thank you. That was excellent.
Yeah, thank you.
Thanks.